My name is Priyanka, this is Sarvesh, this is Emma. We wanted to present a reliable way of measuring body fat and hydration. So basically wearables are obviously getting much more popular. Most of them take advantage of accelerometers and tell you your heart rate and maybe your pulse ox, but a couple of very useful variables that aren't really commercially available are measuring kind of the result of all your hard work, which is kind of decreasing your body fat, and another important variable is your hydration. Really important for runners to make sure they're drinking enough water while they're working out. So a traditional way of measuring body fat and hydration is bioelectrical impedance. So basically by transmitting a small current through one part of your body and measuring it through another, you can find an impedance that corresponds to your body fat and total body water content levels. And so this is fairly accurate, but it's not quite precise enough to be useful on the fly, like maybe while you're in the middle of a run. So we added another optical method to sort of have a redundant set of variables that can offer a little bit more of a precise result.
So for the optical method, we are using infrared LED, which has an emission maximum at 940 nanometers. The body fat has a maximum absorption at that wavelength, and we're measuring the optical interactance at this wavelength by using a emitter detector pair. And from this optical interactance, we have plugged it into the regression equations which gives us the body fat and skin hydration. So we have a prototype of the proof of principle device, and if you just put your arm on the device, you get your body fat and the skin hydration. We'll talk about the statistics.
So we actually made our own regression equations for both body fat and total body water for both male and female subjects. So a user would just have to input their age, weight, height, and gender. And using these equations that we fitted to a commercially available results from a scale, we were able to find these regression equations, and we found that the results that we were getting were actually incredibly close to what we found in the error between the hydration and the hydration we were getting on the scale is very low, and that was the same with body fat. So the percent that these values that you would get with this device would be accurate are close to 95 to 96%. So with more subjects, we can refine our regression equations a little bit and hopefully make this device just as accurate as the bioelectrical devices.
So the idea of this project is that instead of using the electrodes in normal brain-machine interfaces, we're actually using optical imaging. So we genetically engineered a mouse to produce GCAM protein, which is fluorescent when the neurons fire in the brain, since it's sensitive to calcium dyes. So what we can do with that is we actually have some imaging, and we actually image the mouse in real time while it's running on this two-dimensional treadmill that we built. So what happens after that is we get this raw image, we select the type of cells, and then we can actually create a neural population. So after doing appropriate stabilization of the moving artifacts, you actually get a pretty good activity diagram of what's going on in the brain. So without touching the brain at all, you can actually see which neurons are firing and where the sort of functional clustering is in the brain. And as a result, you can sort of tell what's going on when the mouse is running and when it's not. So the result of this is we were able to get over 90% accuracy for telling when the mouse is running or not without even looking at the mouse and only looking at the brain itself. So that's what we have.